Hey everybody, today we're going to talk about a technique that you can use to determine the concentration of an unknown substance. Let's say you work in a lab, like I have a friend who does this, and he runs toxicology screens. So he runs drug tests in urine and blood samples, and he has to figure out how concentrated certain substances are in the blood and the urine. And if you don't know, is there a way to figure it out? Because all this stuff is dissolved into the solvent, so it's very difficult. Well, actually, there's a technique that you can use called Beer's Law. Beer's Law is basically a way for you to test how much concentration there is in a substance. But it requires a little bit of work, and I'm going to explain this to you because we're going to use this in one of our labs here. Here's how this process works. If you shine a light through a substance, whether or not that substance has color, faint color, dark color, whatever, the amount of light that gets absorbed into the substance as the light passes through it is directly proportional to the concentration of the substances in the solvent. So basically, the higher the concentration of the substance, the more the absorbed light. And the lower the concentration, the less absorbed light. And there's a special instrument that we use called a colorimeter that we can use to perform an experiment to determine how much light passes through a substance and translate that to a concentration. What you do is you set up a graphical relationship for any solute dissolved in a solvent, and you know what the solute concentrations are, and so you graph the solute concentration versus the absorbance, and you can plot it on a graph and run a linear regression, and then you can use that line and the equation of that line to figure out the unknown concentration of a sample. Now, this is all fairly abstract, but I'm going to show you a couple of examples here of what it looks like and how we can use Beer's Law to calculate an unknown concentration. Check it out. So inside the colorimeter, you have a sample of solution in what is known as a cuvette. It is this long rectangular looking thing, and it holds the liquid. What happens is that the light comes out from the light source, we call that the incident light, passes through the solution, and the transmitted light on the other side is going to be weaker or fainter than the incident light. And then the sensor, which absorbs the transmitted light, basically determines how much absorbance happened when the light passed through the liquid. Well, what you do then is you take the absorbance values that are spit out from the colorimeter and you plot them versus concentration. And so the concentration's increasing, this is my independent variable, and the absorbance is plotted on the y-axis. Now, each one of these data points you see on this graph represents a different sample of known concentration and its absorbance, and then another concentration and its absorbance, and another concentration and its absorbance. And so what you get is this scatter plot graph and perform a linear regression or a best fit line, and we can determine what the slope and the y-intercept is of that line and get an equation in y equals mx plus b. Now, as long as you keep the solvent the same and the solute the same, then you can figure out what the unknown concentration of. Let's say the absorbance of this substance is 1.05. It is an unknown, but we know its absorbance is 1.05. So we go up to just past, maybe this is 1.05, and you go across and down, and you can figure out the concentration. Or you could literally stick this into the equation and solve for x. You see, in the y equals mx plus b equation, the y variable is the absorbance, which I will abbreviate ABS, and the x here is the concentration. So I will abbreviate CONC. So if I stick 1.05 in to this equation, and I solve for x, I can determine precisely the concentration of the unknown. So what I did is I subtracted this number onto this side so I can isolate x, and then I divided by the 0.09034, and I got a concentration of 111 micromolar, which is this symbol down here, the concentration. It's not in molarity, it's in micromolarity, so that's a really small concentration. But we predicted it would be just slightly past 100 because I drew that line across and then down, and it was just past 100. Now I know exactly what it is. It's 111 micromolarity. Here's an example of an actual Beer's Law experiment that I ran in an AP chemistry class a few years ago. So as you can see, I've prepared these different solutions, 1, 2, 3, 4, 5, 6. So I have 6 solutions, and I tested their absorbance in the colorimeter, and this is what I got. So when I plotted absorbance versus concentration, and I performed a line of best fit, the Vernier software spits out the y equals mx plus b formula for you. So y equals mx plus b, where m is 1.794 times x plus the y-intercept is 0.01052. And now I can test an unknown concentration because I know the absorbance of my unknown is 0.694. So I plug that into y and I can solve for x. And if I solve for x, I get an answer of 0.381 molar, which is my concentration of the unknown solution. And I was able to do that all using Beer's law and a colorimeter. Well, that takes care of this video lesson. Thanks for watching.